Hello, and welcome to the video accompaniment to Chapter 2, Section 1 of our text, the first video of this chapter. And as the first section of the chapter, there's going to be a lot of terms and definitions here, and it's important that we understand those terms and be able to do a few things involving sets and subsets. So if you haven't already, make sure you read through this section of the text, familiarize yourself with the definitions, and look at a few examples. After this, we'll be able to determine when two sets are equal and understand what equality of sets means, be able to find the cardinality of a set, define a set using set builder notation and understand how set builder notation is used. We'll be able to determine when a set is a subset of another set. We'll depict sets using Venn diagrams, and finally we'll compute the power set of a set. And with this video, we have an activity alert, which means throughout the video there will be some activity problems that I'll have you work on along with the video. So make sure you have that out as you watch this video, and to stop the video when I give you the indication that that slide has to deal with an activity. All right, let's get started. Recall that the definition of a set is rather simple. It's just a collection of objects. When we have a really simple definition like this, it'll be easier to understand at first, but later on when we get to the last, probably the last video of this chapter, we'll see that there are some problems with that definition, but for the most part, definition of set as a collection of objects will work for the purposes of this class. So what we'll do here is just look at an example of some sets and determine if they're equal or not. So here we have these two sets x, y, and z, and b, y, z, and x. And an important thing to understand about sets is that they are an unordered structure. So saying something like x, y, and z as the set A and b, y, z, x, that these two sets are really the same thing. In this case, A is equal to B because they contain exactly the same elements. There's no notion of order to them. They just need to contain the same elements to be equal. Take a look at another example. Be the set of all integers greater than or equal to 1, and B is the set of all natural numbers. And remember, the symbol we use for the natural numbers is n. And if you look at the definition for natural numbers, you'll see that these are all, one way to describe them is the counting numbers. So 1, 2, 3, right? N is, let me write, oh, I'm having some issues with that. Let me change the setting here. B. Right, so N, boldface N, is this set. We'll define it using an ellipsis. 1, 2, 3, and so on. It's an infinite set because it never ends. And this ellipsis just means continue the pattern that's been established. So on one hand, we have the set of all integers greater than or equal to 1. On the other hand, we have the natural numbers, which is described here. However, all the integers greater than or equal to 1, this is exactly this set of natural numbers here. Right? It's just two different ways of describing the same set of objects. And that's really what set equality is. When two sets are equal, it really just means there are two different names for the same thing. So here A is equal to B again. See another example. Here A is the set containing the empty set, and B is just the empty set. So this is something I've seen students struggle with in the past, is understanding that sets, right, they're just a collection of objects, and objects is a very, vague term. An object can be anything you can think of, including sets themselves, right? It's sets themselves are objects and therefore can belong to other sets. So here A is the set containing one element, namely the set that contains nothing. So this is the set containing the empty set. And B is itself just the empty set. So B is the set containing nothing. So here, like I said, A has one element in it, the empty set, and B has no elements. And so certainly these sets are not equal. A is not equal to B here. because again, A, we have the empty set is an element of A, and B, there's nothing. Nothing is an element of B because it's the empty set. And so we can say here that A is not equal to B. As we saw in the last example, sometimes sets can be elements of other sets. Now this can be very confusing for students, just figuring out whether an object belongs to a set or not, or whether maybe it's a subset of that set. So for this, I like to go through the following example. I'll give you these 5 sets. So A is the set containing the set 1 and the set containing 1. B is the set containing the elements 1, 2, and 3. C is the set containing 1 and the set containing the empty set. D is the set containing 1, 2, and the set containing 2. And E is the set containing the empty set, the set containing 0, and 0. And so we'll just go through a few statements and determine if they're true or false. So this first one, 1 is an element of A. So we want to determine if 1 is indeed an element of A here. So let's see, let's go to our set A and see, is 1 an element of that? Well, remember, A was the set containing the set 1, set containing 1. So A has one element, namely this one. 1 and the set containing 1. That this element is an element of A. That object, that set, is an element of A. And if you look at how the braces are used, that's the only set, that's the only element in the set A. And so, no, it does not contain 1. 1 is not an element of A. It's an element of this set that's inside of A, but it's not an element of A. So this statement is false. Here we have the statement, the set containing the empty set is a subset or equal to A. All right, so the set containing the empty set does, so the question we should ask here, we're asking a statement about being a subset or equal to another set. And so what we want to ask here is every set in here, or rather is every element here, is every element in this set also an element of A? That's the question that we're asking. That's what subset means, is that every element of this set, of the left set, is an element of A. So here on the left we have the set containing the empty set, so this has just one element in it, namely the empty set. And so we'll go over to A and see, is the empty set an element of A or not? No, we already talked about this. A only has the one element, this set. And so the empty set does not appear as an element of A, and so therefore the set containing the empty set is not a subset of A. So this one is false as well. What about, all right, so same thing on the left, the set containing the empty set, is this a subset or equal to C? So we'll go over to C, and again we'll ask ourselves, is every element of the left set, so is every element of this guy also an element of C? So this guy on the left just contains the empty set, so we ask ourselves, is the empty set an element of C? I'll write that down. Is the empty set an element of C? And so we'll go to C here. C contains two elements, namely 1, the number 1, and the set containing the empty set. So C, an element of C, is the set containing the empty set. However, the empty set itself is not an element of C. It's an element of a set that's contained in C, but nevertheless the empty set is not an element of C, and so this one is false as well. Part D, the set containing 2 a subset or equal to D. So again we ask ourselves, does every element of the left set also an element of the right set. So on the left set we have this set containing 2, so the only element there is 2, so we ask ourselves, is 2 an element of D or not? So we'll go over to D and analyze D. D is this set that contains the number 1, 2, and this set, the set containing 2. So does D contain the element 2? Yeah, it's right here. It's sitting right inside D there as an element. And so this one is true. Every element of the set containing 2 is an element of D. Lastly, we'll look at this one, E. Again, the set containing the empty set, is that an element of E or not? So for is an element of this symbol, right, we're just asking ourselves, does this thing here, this object on the left-hand side, does this show up in E? Is this an element of E? So we go over to E. E contains the empty set, the set containing 0, and 0. So are either one, any of those things the set containing the empty set? No. This one is false. Sorry, I almost drew that like true. That's false. Right? It's true that the empty set, we could say that the empty set is an element of E, because when we go over to E, we see the empty set right here, but the set containing the empty set is not an element of E. Now, while it's easy to understand a set when it's defined by listing its elements, some sets can't be defined that way. Some sets, it's impossible to just list their elements, or it's very hard to list their elements. And so we need more advanced notation in order to define some sets we'll encounter in this class, and that is set builder notation. So in this slide, we'll take a look at some examples of sets defined using set builder notation, and we'll find their cardinality. So first example, determine the cardinality of the set A, which is defined to be the set of all integers, x, such that x is between 0 and 10 inclusive. So remember how set builder notation works. This first part of it is the things that are being collected. So x, these elements x are being collected, and where they're being collected from. So we're taking all of those, we're collecting integers x that are, we only want to collect those for which this open sentence is true. So we just want the integers that are between 0 and 10 inclusive. So one way we might start this problem is to first just list the elements. Right, we want to determine the cardinality, but remember that the cardinality is the number of elements in it. So it might be helpful to list its elements. And right, and this one, even though we use set builder notation to define it, we could easily list its elements. So all the integers between 0 and 10 inclusive, so 0 is included, 1 is included, 2, 3, and so on, up to the last two elements would be 9 and 10. And so A is really this set. How many elements are in here? 11. Cardinality of A is 11. And you could just count them up by hand if you want. All right, let's take another look at another example. So here A is the set of all integer solutions to the equation x squared plus 1 equals 0. So all the solutions to this equation. This is a perfectly fine way to define a set. It's a set of all solutions. And in fact, sets defined like this are really can really be defined using set builder notation. So the set of all integers, so we're collecting integers, subject to, well, they have to be solutions to the equation x squared plus 1 equals 0. So subject to x squared plus 1 equals 0. So set of all integers such that x squared plus 1 is equal to 0. So these are defining the same thing, and that's why I've used the same name for them. And again, we'll determine the cardinality of A. So maybe let's first just figure out, well, can we list the elements of A? What solutions are there to this equation, x squared plus 1 equals 0, when x is an integer. I'll give you a second. But so what happens if we square an integer? Can it possibly be negative? No, there's no way to square an integer and get, say, -1, which is what we would need to have happen here. We would need complex numbers, imaginary numbers, in order to solve this equation. Integers, there are no integer solutions to this. And so A is empty. So we could draw it like this with just two braces, a left and a right one with nothing inside. It's the empty set. Or we can use the notation for the empty set. Circle with a line through it. I should take a second to say some people like to draw the number 0 as a 0 with a line through it. In this class, I'd say stay away from that because we have, that means the empty set. A circle with a line through it means the empty set. And so we are supposed to find the cardinality of A here, the number of elements in A. But there are no elements in A. Right? A is the empty set, and so cardinality of A is the same thing as the cardinality of the empty set, which contains nothing, and so this is 0. Contains no elements. Let's do one more example here. Determine the cardinality of the set A, which is the set containing the empty set, the set containing the empty set, 1, and the set containing the numbers 1, 2, and 3. So A has, let's count up the elements here. Here's one element. Here's a second element, the set containing the empty set. Oh, it's having a technical issue there. So we have the empty set as an element. We have the set containing the empty set as an element. 1 is an element, and the set containing 1, 2, and 3 is an element. And so this set A has 4 elements, and so that's the cardinality of A. Remember that right now, all we can talk about is the cardinality of a finite set. For things like, for infinite sets like Z, all we can say right now, we don't really have a definition for cardinalities of infinite sets. We'll get to that later, but we need some more tools in order to talk about it. For right now, we'll just say things like that. The cardinality of the integers is infinite. Same thing with like the rationals, right? Cardinality of the rationals, again, is infinite. Now, one weird thing you might notice is that, and maybe you've thought about this before, but the integers, we'll get to this in a second, are a subset of the rationals, but they both have infinite cardinality. So the question you might think of is, well, are they both just infinite? Are there any sizes of infinite cardinalities? Like, can I say that that the cardinality of the rationals is bigger than the cardinality of the integers? Right now, no. We'll just say they're both infinite, but later on we'll get back to this, and we'll learn something cool about infinite cardinalities later on. Now that we've practiced a little bit with set builder notation, I would like you to practice this on your own and discover a little bit yourself through an activity. And so make sure you take a look at the activity sheet that goes along with this chapter. In the activity, we'll start by giving a set builder notation for the even integers. So it looks like this. And what I'll have you do is work through some problems to come up with the set builder notation for the odd integers. And along the way, you'll understand a bit more about set builder notation. Building off of that, we can also define the set builder notation for the rational numbers, like this. So it's a little more complicated, hence why it's a part of the activity. And you'll work through some problems to better understand that definition, why that works to define the rationals. So take a look at that activity before moving on. So in this section, a bunch of well-known sets of numbers are introduced along with notation. Now, you should be very familiar with these sets of numbers, but maybe not the notation that goes along with it. And so in this slide, we're just going to look at an example that sort of puts all these well-known sets of numbers together and helps us practice proper subset relationships between sets. And so we'll look at first just the set containing the elements 0, 1, and 2, the natural numbers, the integers, the rational numbers, and the real numbers. So we'd like to understand the relationships these sets in terms of containment, in terms of subsets and proper subsets. So remember that the natural numbers can be defined by listing, just listing the elements. These are the numbers 1, 2, 3, 2, and so on. And so first off, comparing the set A to the natural numbers, we can see that while 1 and 2 are elements of A that are also elements of the natural numbers do not contain the element 0. And so for these first two, we'll say A is not a subset or equal to that are the natural numbers. So anytime we can say not an element of or not a subset of, we just draw a strike through that symbol, and that means the negation of that statement. So next we'll compare the natural numbers and the integers. So natural numbers here, the integers, right, we could describe them as positive and negative whole numbers, including 0. And so this, we can list these, but we'll need 2 ellipses. So let's say -1, 0, 1, 2, and so on past that. So it contains all the negative numbers, negative whole numbers as well as the positive whole numbers, and the element 0. And so we can see here that the natural numbers are a subset of the integers. This is telling us the natural numbers are a subset of the integers. But actually we can say more, right? Because the integers contain some elements that the natural numbers don't. And so we can actually say more. We can say that the natural numbers are a proper subset of the integers, because the integers have elements that the natural numbers don't, yet every natural number is an integer. Now we'll compare the integers to the rational numbers. Remember, rational numbers, after just looking at that activity, are ratios of integers where the denominator is not equal to 0. Every integer can be described that way. So if I have, say, the integer 5, right, 5 is an element of the integers, then 5 divided by, say, 1 is a rational number because it's a ratio of 2 integers. And so 5 over 1, that's the same thing as 5. So 5 over 1 in rational numbers is the same thing as saying 5 is a rational number. And you can do this, right? 5 wasn't special. We could do this with any integer we want, including 0. Right? 0 divided by 1 is still 0. And so every integer is also a rational number. So what we can say here is, again, that the integers are a subset or equal to the rationals. However, as you might be saying right now, there are some rational numbers that aren't integers, right? Rational numbers are a bigger set than the integers. So things like 1/2 are in the rational numbers, but 1/2 is not an integer. So we can say more again. The statement we already wrote down is correct, but we can say even more. We can say a stronger statement. Oops, I didn't mean to draw that. We can make a stronger statement and say that the integers, z, is a proper subset of the rationals. And lastly, we'll compare the rational numbers to the real numbers. And it's a similar situation. Every rational number is a real number. Remember, real numbers these are actually a lot harder to describe. It takes a lot of work to fully describe the real numbers, but right now what would work is just saying it's all the integers and all the numbers between every integer, right? So all the decimal expansions, everything like this. And so certainly every rational number is a real number, so we can say the rationals are a subset of the reals, subset or equal to the reals. And then can you think of a real number that's not rational? A real number that cannot be expressed as the ratio of 2 integers. Well, we'll get to this later and we'll actually prove this, but something like the square root of 2 is a real number, right? We can find a decimal expansion for it. However, that decimal expansion has no pattern to it, really, and it never ends. And so square root of 2, we'll prove this later, like I said, is not an element of the rationals. And so again, we have this relationship where the rational numbers are a proper subset of the real numbers. And so putting this all together, we know A is not a subset of the natural numbers. However, we can say A is certainly a subset. So we'll list that again. A is not a subset of the natural numbers because of the 0 that's in A. A is a subset of the integers. And then the integers are a subset of the rationals, which is a subset of the real numbers. So we could make a statement like this. And then sort of excluding A here, how all the well-known sets of numbers fit together, what we showed up top here is that the natural numbers are a proper subset of the integers, which is a proper subset of the rationals, which is a proper subset, I sure wish I had an undo button. A proper subset of the real numbers. And so that's how these well-known sets of numbers fit together. Now, one thing that'll be really useful for us when dealing with sets is to have a method to visually depict the sets and better understand the relationships. And this will be this will be really helpful in the next section when we talk about operations on sets, that we can sort of use these depictions to prove things. These depictions are rigorous enough in order to prove things. And so here we'll talk about how to depict sets using Venn diagrams, and I'm sure you've probably seen Venn diagrams before. If not, that's okay. We're going to go through a quick example of how to depict sets using Venn diagrams. So I'll start here by just drawing what's called the universal set, or the universe of discourse. And I'll just draw that as a big square. So this is where A and B are going to fit in. I'll call that U. It's just some set that A and B are subsets of. Next, I'll notice that some relationships between A and B. Notice that they both contain the element 3, but that 2 is not an element. 2 is an element of A that's not an element of B, and what else? 7 is an element of B that's not an element of A. So there's some things in B that aren't in A, there's some things in A that aren't in B, and there's some things that are in both of them. And so I'll depict that like this. So I'll draw a couple blobs. Here's my blob for A. Everything that's in A will go in here. And then a blob for B, everything that's in B will go there. And what I'll do now is I'll just place all of these elements that are involved in A and B in the spot that makes the most sense. So A, so we'll go through just all the numbers here. So 1 is in B, but it's not in A. So that's over here, element of B. That's not an element of A. So 1 is over there. 2 is in A, but not in B, so I'll draw 2 over here. 2. And then 3 is in both A and B, and so that'll go in here. This is what's called the intersection, which we'll talk about in the next section. So 3 is there. 4 is in A, but not in B. So I'll draw 4 over here. 6 is in both of them, so that goes in the intersection again. 7 is in B, but not in A. Same thing is true for 8. So 7 and 8 go over here. And then A contains the element 9, but B does not, and so 9 goes over here. And so this is how a Venn diagram works. The blobs represent the sets, and the little dots represent elements, and those are labeled with what the element is. Now, we do have this universe of discourse here. Usually that'll be given to us in a problem, what the universal set is. In this case, I didn't give you one. There are a couple things we could take as the universal set. We could take, say, the integers 1 through 9, or we could take all of the natural numbers, or we could take all of the integers or real numbers or whatever we want. We could take those. So long as A and B are subsets of the universal set, this picture makes sense, and we can use it. Even when we can't list all of the elements of a set, we can still draw Venn diagrams for them. We just won't draw elements in it. And this is useful for describing relationships between sets in terms of subsets or not subsets. And so in this one, we'll just look at all of the well-known sets of numbers and put those in a Venn diagram. So here I'm going to draw my universe of discourse, my universal set U. Universal set U. I'll make this really big. And I'll actually take U to be the real numbers here, because I know that everything, all these well-known sets of numbers fit inside of the real numbers. So that'll be my big outside set, is the real numbers. The next biggest set we have is the rationals. And so maybe I'll draw a big blob for the rationals. This is where all the rational numbers sit. Inside of the rationals are the integers, but we know, again, it's a proper subset. So notice how I'm drawing my blob so that there's some stuff outside of the blob, but inside the rationals. So these would be the integers. And then the smallest well-known set of numbers that we deal with is the natural numbers, which sit inside of the integers. So we're really just visually depicting those subset relationships that we had before. And so one thing we could do here is, why not? Let's put some elements down. Obviously we can't draw every single element that's in the real numbers or the rationals, but we can do a few examples just to illustrate that these are proper subsets. So remember, the real numbers, like square root of 2 was a real number that was not a rational, and so that would sit out here. Also, numbers like Euler's constant e or pi cannot be expressed as a ratio of two integers, so those are real numbers that are not rationals. An example of a rational number that's not an integer, I said something like 1/2. Yeah, 1/2 would work, or maybe 22/7, which is a decent approximation for pi, but is not actually pi. Would be a rational number that aren't integers. Integers that aren't natural numbers, well, 0 is an integer. Same with like -1, and those are not natural numbers. Remember, natural numbers inside of here would be like 1, 2, 739. Anything like that are all sitting inside the natural. So these are all infinite sets, but they sit inside of each other like this. And we can depict them using a Venn diagram. The last concept I want to talk about in this section is the power set. So the power set is kind of like an operation on a set. And what it returns is the set of all subsets of that set. So here we have the set A equal to the set containing the elements 1, 2, and 3. And we want to find the power set and the cardinality of the power set. So A is a set, and there's many subsets of that set. So for example, the set containing 1 and 2 is a subset of A, because 1 and 2 are both elements of A. Every element of the set containing 1 and 2 is an element of A, the set containing 1, 2, and 3. But also, like the set containing 1 is a subset of A. And in fact, this might be a little bit weird, but A itself is a subset of A, because every element of A is also an element of A. That's something that's always going to be true. The set itself is always a subset of itself. Another thing that's always going to be true is that the empty set, the set containing no elements, is always a subset of every set, and in this case A. So why is that true? I want to talk about that for a second. Empty set, subset of A. Remember, we can define the subset relationship through an implication, right? This means for all x, if x is in the empty set, then x is in A. That's what subset means. Every for all x. So this statement, if x is in the empty set, or this open sentence, if x is in the empty set, then x is in A, is true for every single value x. That's what it means to be a subset. So in this case, if x is in the empty set, that's the hypothesis of our implication, well, there are no elements in the empty set. And so x is never an element of the empty set. That means the hypothesis of this implication is always false. So remember, if the hypothesis of an implication is false, then the implication is true. And so that means that, this implication is true, and so it is a subset of A. We call things like this, where the hypothesis is always false, vacuously true. It's vacuously true. So A has a lot of different subsets, and we can list all of those in a set. So power set of A, that's a pretty poor P, but that's my curly P. Power set of A. So this is a collection of all subsets. So the empty set is in there. We said the set containing 1 is a subset. The set containing 2 is a subset. Set containing 3 is a subset. We can do the 2-element subsets. Set containing 1 and 2. The set containing 1 and 3. Set containing 2 and 3. And the set itself, 1, 2, and 3. Instead of saying A, 1, 2, 3. I'll write it out by listing. And so that's what the power set is. Every element is a set, specifically a subset of A. And so now we can count all the elements here to find the cardinality of A. P's still a little bit rough, maybe a little bit better. And so we can count all the elements here. There's 1, 2, 3, 4, 5, 6, 7, 8 elements in the power set. And so the cardinality of the power set is 8. Notice here that the cardinality of A was 3. And did it really matter what the elements of A were? Or is this going to be true for every set A with cardinality 3? Right? If A has 3 elements, then its power set will actually necessarily have 8 elements, no matter what the set was. So this sort of begs the question, is there a relationship between the number of elements in the set and the number of elements in the power set? Cardinality of A versus the cardinality of the power set. And so that's the subject of the activity I'm going to have you work through the problems in the activity sheet to determine a formula for the power set of A in terms of the cardinality of the original set. And that's it for this video. So once you work through that activity, you're done and you can move on to the next section.